Okay, chapter 3, section 3, day 2. We're still dealing with this ax squared plus bx plus c, and we're focusing on how this bx term is affecting the location, ultimately, of my quadratic, my u shape. And ultimately, this bx is going to shift it left or right, whereas the c term is going to move it up or down. A still only affects the shape, the steepness, and whether it's happy face or sad face. Okay, so the main punchline again being this negative b over 2a, we're going to use that to be applied to our example for today. And our example, we're actually going to be graphing. Okay, so here is our example that we're going to be focusing on today. In this instance, we're given this quadratic equation, this function, and I know it's a quadratic. I know what kind of shape it's going to have. I know it's going to be this kind of U shape, whether it's a happy face or a sad face. I know it's going to be that shape because of this x squared going on here. This x squared being the highest degree in this equation is going to force it to have one of these shapes. And so graphing it is the way I do it. Now, what can always be done, I can always just put together an XY table, throw a bunch of X values at it, and ultimately I'll get one of these shapes. But being able to minimize the number of X values I throw at this thing can be valuable, because then I can limit my own work and ultimately just graph the interesting part of this graph. Because when it comes to a U shape, say for instance with this guy right here, if I were to choose X values that were too far to one side, it would appear like it'd be a vertical line, or at least a very, very slight curve, right? Or if I chose on this side X values, and then again, it would appear to be vertical. So really what I want to do is I want to choose X values that will be lined up somewhere towards the middle of basically the interesting part, the curve, the U part of my U shape. All right, so I want values that will center it around what we call the vertex. The vertex being the extreme point of whatever U shape I'm dealing with, happy face or sad face. And so if I can identify values around that vertex, then I can get away with just having like the vertex itself, pick a point to either side, and now I have my U shape. And so I can get away with as few as 3 coordinate points and be able to create my U. And so the trick with that is identifying where that critical point, that vertex, is located. And that is where we're going to be using the strategy of the negative b over 2a. Negative b over 2a in this equation, we'll be able to identify where that axis of symmetry is located on a coordinate grid, but also where that vertex would be located. And if I can identify that, then it'll be very, very quick and easy to identify points around that. Now, another strategy we're going to be using for graphing this has to do with this term right here, symmetry. Okay, symmetry. These U shapes are symmetrical, meaning that if I were to graph this axis of symmetry right down the middle of it, okay, I'd be splitting it up into 2 reflected halves, basically. Okay, splitting it right down this middle, every point on this side of a given parabola will be perfectly reflected over that axis of symmetry, that mirror, over to the other side. Why will that be valuable? Because when it comes to an XY table, if I were to say graph my vertex point, but then I chose like say this point right here, okay, and I did my calculation, it spat out this coordinate point, I would know that coordinate point has a perfectly reflected value on the other side. That's another strategy we're going to utilize here with this. So we're actually going to be able to limit our work significantly. Okay, so let's jump into this problem and deal with that negative b over 2a strategy. All right, so as what you will see on a section assignment, what you'll see in this chapter's test, you'll be given some sort of quadratic function. So we were given this in this example, f of x equals 3x squared minus 6x plus 5, right? So this is pretty typical of something you might see, particularly in this section, but yes, anywhere on a test, you might come across this as well. And you'll be asked to graph this function. And again, I'll take the time to emphasize that anytime you're asked to graph a function, you can just chuck a bunch of x values in this with an xy table, literally anything you want for x. And as long as you do the calculations correctly, you'll be creating a series of coordinate points that if you graph those coordinate points, you will ultimately get the shape of the graph. But if I'm blindly throwing x values into this function, it may take a lot of x values to ultimately get the correct shape of the graph, even if I know that this is going to be a parabola based on this x squared. That's a valuable piece of information to know, but still. So the way I can kind of streamline or make my methods more efficient, like where do I begin for picking x values to plug into this function, has to do with this little mini formula that we talked about yesterday, negative b over 2a. Okay, the reason why this will be important is because it's ultimately going to tell me what x value I want to begin with for my xy table. And if I know where to begin, I can be very strategic about just picking, like, all right, if I know I'm going to start here, I can just pick a point on this side and then one on this side. And now I have my U shape. Okay, and now I've reduced down my work to finding 3 values, which is far more convenient than just chucking a bunch of values into this blindly. Okay, so in order to use this negative b over 2a, I'm going to kind of need to know what a, b, and I don't need it in this case, but what c is. And so again, I'll take the time to point out that a is the coefficient that's attached to x squared, b is the coefficient attached to just x, and c is going to be the one that has no x attached to it. As long as you can identify these values, this part's really quick and easy. Just be, again, careful with the sign attached to that coefficient. So for instance, that positive is attached to the 5. This negative is attached to the 6. So b is a negative 6. That tends to be something that a lot of students lose track of. Just be careful with it. And then this 3 is positive, so a is a positive 3. Okay, so there's a, b, and c. I don't need c in this instance, but anyway, when I plug into this little mini formula, right, my suggestion is to keep the negative sign, keep the fraction. You're basically just substituting or replacing a and b with their corresponding coefficients. So b, in this case, is a negative 6. So many of you would be able to do this in your head, but if I have a negative, this will ultimately become positive. But again, if you're struggling with that, it can help to literally write it out, and then it'll be a little more obvious that this is going to turn into a positive. And then the denominator, I have 2 times whatever a is. And so a in this case is this positive 3. So it's going to be 2 times 3 on the denominator. All right, that's just the substitution part. Many of us can probably skip to this piece right here, which is to say, like, all right, what's my numerator and then what's my denominator? Well, on the numerator, a negative 6 becomes positive 6. And then the denominator, again, many of us would be able to do this in our heads, but 2 times 3 would also give me a positive 6. Again, the most common mistake for this one would be losing track of that negative sign and leaving it negative on the numerator here, but that would be a mistake. Okay, so now that I have my negative b over 2a at 6 over 6, I can reduce that. That reduces down to 1, and this is going to be my negative b over 2a value. Okay, well, so what? So like we discovered yesterday, doing negative b over 2a will give me some number. It will give me a value. But what is the significance of that number? That number tells me, basically, for an xy table for graphing this function ultimately, where I can begin. This will ultimately provide me the vertex. Okay, now this will actually provide me 2 things. First, this will more simply provide me the axis of symmetry, literally the line that will chop my parabola in half. It'll tell me where it's located, left or right, on a coordinate grid. And in this case, it's at positive 1. So if I was graphing this vertical line, I would move right 1 unit. All right. Now, that only tells me where this line that chops it in half is. Now, the vertex can be anywhere on that vertical line. So in order to find out where exactly the vertex is, I need to take this value and I need to plug it back into my original function. This is basically what we would do for an XY table. Okay, so in this case, I'll go ahead and just go right into solving for the vertex like we did in our previous example from yesterday. And so here's our equation. We would have y equals, or we were originally given f of x, but that's just a fancy way of saying y, 3 times x squared. But we're going to replace x with that negative b over 2a value, that positive 1. And then it was minus 6 times x, but again, we're going to replace that with that positive 1, and then it was plus 5 at the back end. This is essentially what we do for an xy table. We'd pick some x value. This is not so random, the x value we've chosen. We've literally found this negative b over 2a being a positive 1. We're going to take that, plug it into the equation with this purpose in mind. By plugging it back into the equation, it's going to spit out some corresponding y value. And then we'll have created a coordinate point. The significance of that coordinate point, it will become the vertex, the most critical point in our U shape. Okay, well, at this point now it's just doing the math, the computation. So just be careful about your order of operations. I have to deal with this exponent first. So 1 squared is 1. So I'll do the long version of the work here. So it'll be 3 times 1 after I do 1 squared, which is 1 times 1, right? And then I have minus 6 times 1. Well, that's going to be a net minus 6 right there. And then nothing happened with the plus 5. That was still plus 5. Okay, so this is just a long version of showing the work. And so now doing this multiplication, 3 times 1, I'm going to end up with 3 minus 6 and then the plus 5 at the back end. Well, now I just have a string of arithmetic I got to do. Just do it in order. 3 minus 6 gives me negative 3. That negative 3 plus 5 is going to give me positive 2. So what's the significance of that value? What we have just done is what we typically do on an XY table, right? We choose some x value to plug into our function, and it's going to spit out some unique value. This has just created a coordinate point. What's the significance of this coordinate point? Because we did negative b over 2a, this will turn out to be what's called the vertex, or the extreme point in a quadratic, our parabola, our U shape. And so our vertex here is going to be the coordinate point, positive 1, positive 2. The 1 coming from our negative b over 2a, the positive 2 popping out the other side of the equation when we plug that x value into the equation. And so that's going to be our vertex. All right, so how are we going to use this to actually graph? So let me back up top here, and I'm actually going to erase this and build an XY table. So keep that vertex point, that positive 1, positive 2 in the back of your mind, because we're going to keep that for our XY table. That actually was half the work that we need done. All right, so again, kind of going back to what you would ultimately need for any graph, that is an XY table of sorts, right? Again, f of x is just a fancy word for y. So first off, we have already created a coordinate point, the most critical coordinate point of our graph, namely the vertex, 1, 2. All right, so this right here was my vertex. That's going to be the extreme point of my U. Now, this was a happy face U. I knew that because of the fact that it was a positive 3x squared at the beginning of my function. So that positive 3 is going to force it to be a happy face U shape. So this 1, 2 is going to be the bottom, the minimum point in this U shape. All right, so here's what you would do for your XY table at this point. I know this is my critical point. Technically, I know I only need 3 points to make a U shape. So just pick a coordinate point less than that value, and then go the same distance the other way and pick a coordinate point bigger. So for instance, let's pick a value less than 1, like say 0. And then let's pick a value greater than 1, like say 2. Okay, pretty innocuous, not terribly difficult right there. But the reason why it's important that I choose the same value below as I do above has to do again with this concept of symmetry. Here's what I mean by that. Because a U shape is symmetrical, everything on one side of the U shape will be perfectly reflected to the other side of the U shape. Because a U shape is symmetrical, whatever value I get for this result needs to match whatever I get here. Okay, I'll confirm that with the mathematics. So let's work through that right now. So again, in both of these two values cases, what I'm essentially doing is I'm just plugging it back into the original equation. And for us, again, that was 3 times x squared minus 6 times that same x, and then plus 5. Okay, and I'm using the same exact equation on this value. It's just going to be a different x value that I plug in. Again, this is like how it's done with any xy table, is I'm taking some function or some value of x and I'm evaluating it in whatever function I've been given. This one just happens to be a little bit longer than some that we've dealt with. Well, in this one, I'm just going to be plugging in that 0 value in for x. That'll make things convenient for solving it. And in this one down here, I'm going to be doing the same thing, but with 2. Okay, so I'm going to just talk through the solution here. Obviously, you would probably want to show a little bit of work here, or at least do this on a calculator. But in this case, 0 squared, the first thing I'd have to do here is just going to be 0. But that 0 times 3 is going to make this guy go to 0. And then in this one, negative 6 times 0, that's also going to be 0. So I'm going to have 0 minus 0, which is still 0. So basically all of that stuff just went away, and I'm left with the plus 5. That is going to give me a value of 5 on the opposite end of that spectrum. Okay, so you can trust that math right there, but we're going to end up, when x is 0, 5 pops out the other side of that equation. We've just created a coordinate point that I can graph. There was a vertex that we went through before. Again, we found that value using negative b over 2a. And then it's pretty much this process again, just plugging 1 in, and 2 popped out the other side. So for this one, 2 squared is 2 times 2, or 4. 3 times 4 is 12. So this first term is going to turn into 12. Negative 6 times 2 gives me negative 12. So I'd have a positive 12 here, negative 12 here. They're going to end up canceling each other. Positive 12 minus 12 gives me 0. And now I have plus 5 at the back end. What do you know? It ends up matching the other value. But again, that makes sense. And here's why. These values should match. Sorry, that probably got busy right there. These two values here. These two values here should match because this U shape is symmetrical. So for instance, if I were to evaluate this equation for negative 1 and go another value less than 0, whatever popped out the other side, it should match whatever's one more than positive 2. Because again, what should happen, this is the extreme point, the vertex. Everything on either side of the U shape should be perfectly symmetrical. So let me jump to our solution sheet so you can actually see that visually. All right, so again, this resource is also on Google Classroom, but let's talk through it anyway. So a little zoomed out here, so let me just bear with me here. Okay, so ultimately here is the graph of our parabola. This is what it will be once we're finished. Now, here's the pieces that we found. First off, using this negative b over 2a, we use that to locate our vertex. Again, we found that to be a positive 1. We plugged it back into the function to find out that 2 popped out the other side. That positive 1, positive 2 gave me my vertex. That's going to be the critical point in this parabola. Now, because it was a positive 3 x squared, that means it's going to be a happy face parabola. So it makes sense that it's going to be opening upwards from that critical point. But regardless of what value I found over here on this side of the parabola, regardless of what value I have, it should be perfectly reflected to the other side of the axis of symmetry. Again, the axis of symmetry here going right up the middle through the vertex of this parabola. Now, when I chose, like, here's my XY table down here. When we found our vertex and we chose a value less than, and then a value greater than that vertex x value. And so when I plugged in 0, 5 popped out the other side. That 0, 5 is this coordinate point right here. Okay, there's the 0, 5. Even though I went through the work of plugging in the positive 2, basically over on this side, searching for where the coordinate point would be, I could actually have skipped that work, because if I know where the vertex is, and I have something to the side of it over here, okay, I know that its reflected point should be directly opposite this axis of symmetry. Okay, In other words, because I did the work here for when 0 popped out 5, then for positive 2, it should also pop out 5. And so if I were to plug in -1 and it popped out positive 9 on the opposite side, then at positive 3, it should also have the same value because it's, again, making its way symmetrically to make this U shape from either side of the vertex. So that's a quick way that you can actually cut your work in half for what you would have to do for your XY table. Okay, and then briefly just discussing it because you were asked about domain and range in this problem. Domain, again, represents the possible X values or how far left and then how far right this parabola can go. This will be true of all our vertical parabolas, all our U shapes, that they'll be able to go infinitely left as well as infinitely right. What that basically means is that there is no limitation on what X can be in these quadratics. It can be as big as we want or as small as we want. So another way to say it is domain is all real numbers. Okay, that will be true of these quadratics we're graphing. For range, range is the possible Y values or how far up and how far down this graph goes. Well, up, obviously, in this case, because it's a happy face parabola, it goes forever upwards. Okay, that's probably a little bit more obvious than the left-right. But the lowest this graph goes is right here. And in this case, that would be positive 2. Okay, which is part of the vertex. In this case, Y is everything bigger than or equal to positive 2. So that would be the range in this case. All right, one last example problem that you had for this section. I promise this one is super fast. Okay, so our last example from this from the section, we're given this following quadratic equation. Again, I know it's a quadratic because of the x squared. This one will happen to be a sad face because it's a negative 4x out in front, and it's a little bit steeper. So not only is it sad face, but it's on the steeper side. Okay, but all we're asked here is we're given this quadratic equation and says, does it simply have a minimum or a maximum? Well, here's the simple answer. It has everything to do with this leading term a. A, again, being the coefficient multiplied by x squared. So in this case, A is going to be determining whether or not it's happy face or sad face. So in a happy face parabola, you're going to have a minimum point. Because in the happy face, there is a minimum. There is no maximum here because it goes forever upwards. So there is no maximum number because there's always some number bigger than that value. But there is a definitive minimum value in this case. On the flip side of that coin, if you had a sad face parabola, like you're going to have in this problem, but if you had a sad face parabola, then you have a maximum. Definitive maximum. There is no minimum here because, again, it goes infinitely down. Okay, so the long and the short of it is this. When they ask you about minimums or maximums, you're just paying attention to, is it negative or positive in front of the x squared? This one's negative, making it sad face. And sad face parabolas have a maximum. The answer here would be it's a maximum. Now, if it asked you something a little bit deeper where it said identify what the maximum coordinate point is of this quadratic, that's another fancy way of saying identify the vertex. And that's where you would use the procedure we've done before of basically use the negative b over 2a to identify the x value, plug it back into that equation to find out its corresponding y value, to create that vertex point. And that's how you go about solving it. All right, I'm going to go ahead and stop recording.